Okay. Hello, I'm Zhe Sun. I'm a data scientist in ING Wholesale Banking Advanced Analytics team.
Yeah, so my mic is on.
Yeah.
You can introduce me.
This is Daniel Van Ende. He's the data engineer in our team. Thanks for coming our talk, large-scale fuzzy name matching with ML pipeline in batch and streaming. Yeah, I know it's 5 p.m. It's the second day. I hope you still have energies, and fortunately, we are not the last talk. And I promise you there is no complicated mathematical formula here. And ING is the largest bank in the Netherlands. It's also a worldwide financial institution. ING has business in over 40 countries and with 50,000 employees. It has around 40 million customers, so including both retail customers like you and me, and also commercial customers like companies. Daniel and me are working in the ING Wholesale Banking Advanced Analytics team. And this is our Logan, catch it down. And we deliver the algorithm-based data product. So various of different roles in our team, from UX designer to data scientists and data engineers. We love playing ping pong after lunch, and we have very international environment. So from the map, you can see that the colleagues are from almost all the continents except Antarctica. And yeah, we are expanding significantly. So if you have life experience or working experience in Antarctica, and if you are interested about us, you will be definitely hired. Okay, yeah, stop branding. And so about name matching. As a multinational and a multi-product bank, ING naturally faces data consolidation tasks across different internal and external data sources. Here's the example. So we get credit rating data from Moody. Yeah, Daniel has a AA company. Names Daniel Dutch BV. By the way, BV is a kind of legal form, company legal form. And my company is even better. I have a AAA company. And we want to link them with the ING customer data. Yeah. And unfortunately, for the Moody's data, there is no ING customers identifier. So name is the only way to link the two data sets. And as you can see, the name of the same company from the different data source might be slightly or significantly different. So we need a fuzzy name matching model to link the data set. Okay, so let's define the data science problem. We have two data sets. So names to be matched. So it is, which is the Moody's credit rating data set in the previous example, and the ground truth data set, which is the ING customers records in the previous example. For the names of the two data sets, we compute the pairwise similarity. And for each name in the names to be matched set, we pick up the most similar name from the ground truth data set. Yeah. So this is a data science problem. And here the function f. Here the function f is the similarity functions. So what kind of similarity metrics should we choose? So in ING, the scale of fuzzy name matching problem is not small. So one of the use cases matching 160 million names to another 10 million names data set. So it's around 1.6 multiplied 10 power 15 times similarity computation. Due to the limitation of the data deployment in that product, it requires to be finished in a couple of hours. So some popular approach, such as Levenshtein distance, will be very, very slow. For the sake of speed and accuracy, we choose the token-based cosine similarity as a similarity computation. And the pipeline is basically the pre-processing, vectorization, cosine similarity computations, and candidate selection. Yeah, I will demonstrate this pipeline. Again, we have two data sets with names. Step one is pre-processing. Basically, it normalizes the names, right? Like such as remove the punctuations, convert the letter to the lowercase, and handle the legal form and the abbreviations. So the normalized names will be tokenized and transformed as Spark vector. So this is a step two vectorization. So one name corresponds to one Spark vector, and the whole data set will be a sparse matrix. Next step is to compute the pairwise cosine similarity. And for each name in the name to be matched set, we ranking the similarities and pick the top candidate. And finally, we have a supervised classifier to pick the best candidate by using the features extraction from the names. And if you map this into the Spark pipeline, then very clearly that steps of pre-processing, the vectorizations, and the last step, the candidate selections, they are standard map operator. But for the cosine similarity, it's a bit complicated. So I should mention here that when we compute the pairwise cosine similarity of two sparse matrices, it's actually equivalent to do the sparse matrix multiplications. And unfortunately, there is no native sparse matrix multiplication. So we developed our own framework. Here, the two sparse matrix, the name to be matched and the ground truth. P and M are the number of names in the two data sets. And K is the size of the token dictionary. We have an X-executor sparse cluster. And fortunately, the ground truth sparse matrix, the size of it is small enough to stay in the memory of each executor. So first step, we broadcast it. And then we distribute the left matrix to each cluster. Next, to distribute it to each executor. Then next, inside each executor, we do the sparse matrix multiplications. Here we use Python SciPy package. And the result will be ranked, and we sort it and get the top-end result. Finally, we collect the result, get the final top-end match candidates for each names. In this way, it's X times faster than a non-distributed way. And we can do even better. In Python SciPy implementations of sparse matrix multiplications, it first scans two matrices to decide the number of non-zero elements. But actually, we can skip this step because here we know that for each name, we have at most n candidates. Yeah, we know the size. So here's another way to speed it up is we combine the multiplications step and the top-end selection step as a one single operator. So we hacked the SciPy implementations, and we implemented it by C++, and wrap it by Python. In this way, we use less memory, and it can it's 40% faster. We wrote a blog post here and also open source it. So if you have similar requirement, welcome to use it. All right, so as you can see, we have a kind of relatively complicated cosine similarity and ranking solutions. But fortunately, Spark provides us a very powerful pipeline and customize the stage so that we can easily wrap it. So here is the pseudocode. We can create a cosine similarity matcher model. And in the initializations, we broadcast the ground truth sparse matrix. And in the transform stage, which is exactly doing the sparse matrix multiplications, the name to be matched data frame first converted as a RDD and does all these C++ Python tricks in each map partition. And finally, the results are collected and converted to the data frame. And for the whole pipelines, we can easily put them together as shown here, including like pre-processing, tokenizations, n-grams, count vectorizer, DF-IDF, cosine symmetry matchers, and supervised transformer. And one thing can be noticed that besides the cosine symmetry matchers, these 4 stages are all customized stage. And thanks for the Spark, we have a very elegant and easy maintainable way to build a machine learning pipeline. So we put them together. So 160 million names to match 10 million ground truth names on a 10-node cluster, small cluster. We can finish it in 5 hours. So it's approximately 8,000 names matched per second. Okay, this is the story of the batch, and I will hand it over to Daniel for the streaming story.
Yeah. So thank you very much, Zhe. So the use case we've shown you so far is matching 160 million names to 10 million. That was the base use case that we actually started with developing this algorithm. But very quickly, as we started working with this, we started thinking, well, this isn't a very specific use case. People all across the world are actually trying to do similar stuff, match names to some sort of ground truth they have. And we started reasoning about an API that we could somehow expose to other teams with either within ING, but maybe also externally. This use case does change things slightly. So a couple of things to mention and to take into consideration. So the idea we had in mind was to expose sort of a search bar that you could type in a name, and it would match that name to something in the ground truth. So given that, you'd expect the number of names to be matched to be much, much lower than what we were dealing with in 160 million. It also leads us to point number 2. We'd like near real-time results. If you're typing stuff into Google, you're not going to sit there waiting for 5 hours for all of your names to be matched. You want it to be quick. You want it to be somewhat responsive. The third point is also super, super important. The ground truth may change. We can appreciate that not everybody is that interested in ING's customer records, maybe from competition perspective. So we'd like to also make it possible to exchange your own ground truth in there. And finally, the most important part of this, we don't want to have to change our code base. So we don't actually want to have to make major changes in the algorithm that we built because we spend quite a lot of time optimizing here. So that very quickly led us to structured streaming. And this was actually the quote that basically convinced us, particularly the part about not having to reason about streaming. We know that streaming is very complex. And we just wanted to see, hey, can we get this to work without getting into the really nitty-gritty details? And we just wanted to keep our code base as simple as we possibly could. So at a very high level, what our setup now looks like is this. So our names that people want to match arrive on a Kafka topic. We've built a Spark application, a Spark structured streaming application, I should say, that wraps around the Spark ML model that we built in the past. It does its magic, it matches the name, as we showed before, and then it will just output that onto Kafka. Again, a different topic. In terms of code, what did it actually mean? So as you can see, it's actually quite, it's quite short. The first couple of lines are just initializing the name matching object we had. We fit it on your ground truth, so you can decide what your ground truth is. And then we start hooking up Spark to Kafka. So I've left out a few configuration options here, like the SSL setup, because I didn't think it was very relevant. But it's really, really quite simple. It's really quite elegant. Then the next step is basically to say, okay, we're going to do some pre-processing on the names that come in to make sure that the algorithm can understand what's actually being given to it. And then using that trained name matching object, we're going to say, okay, let's transform. And we're going to do some sort of post-processing to make it some sort of nice formatting for our downstream stages. And then we're just going to write back out. Super, super simple. There was one thing that we we didn't really expect. So as some of you might know, Spark structured streaming doesn't allow you to do any actions. Now, actions usually are things like count, collect, show. Those are the actions you'd be expecting. So in this beautiful piece of code that Zhe showed you earlier, there's also an action, namely this one. And this is a pretty nasty one, actually. So the problem is we need to actually convert our data frame into an RDD because PySpark doesn't have map partitions natively on data frames. It is on RDDs. So to get around this quickly, we said, all right, PySpark doesn't support this. How can we actually get this function to run? Let's use a UDF. So once again, we were really surprised, really quite happy with how simple this code actually turned out to be. We just basically wrap our function and we add it to the data frame that we want as output, and winning. This works. So we're done, right? I mean, end of the talk. Well, we're a bit short. However, you can probably see where we're going with this. As good data engineers and good data scientists, we want to make sure and we wanted to see what the effect of this change would be on the algorithm. So we started actually monitoring some of the performance. So this graph is basically comparing the two methods that we've shown, so using the RDD map partitions and using the UDF. So on the horizontal axis, we've mapped out different ground truth sizes, varying from 1 million to 12 million. And on the vertical axis, you can see the actual transform time for a single name. First disclaimer, we've claimed already in this talk that we could match 8,000 per second, and you're now seeing half a second for a single name, so you're like, what the hell's going on here? So the 8,000 per second is in a complete batch situation. So all of the optimizations that we did with setting the partition size right, getting all the executor settings right, those were optimized to actually reach that 8,000. The real important thing here is that we are comparing the RDD method, as we've called it, to the UDF method. So as you probably already know, the UDF has, especially a Python UDF, has quite some overhead. So we do see, for instance, for the 1 million names that, yeah, it's a bit slower, but we can deal with it. What's more concerning is that as the ground truth size increases, the difference also increases quite a lot. By the time we get to 12 million, the difference is over a factor 2. So our data set is 12 million, so we could probably live with this, but we were quite curious to figure out where this was coming from. So the reason that this is actually happening is caused by how Python UDFs work in Spark. So for most of you, this probably is something you already know, but just to make sure that everybody understands what we're talking about. So Spark is a JVM-based framework, written mostly in Scala. So if you have a driver program, let's say a PySpark shell that you're just trying stuff out, it actually is communicating with a JVM-based Spark session underneath. And that JVM-based Spark session will then start communicating with the data frames, or the partitions, I should say, on each executor, which are also JVM-based. If you then define a Python UDF, Spark actually needs to get the data out of the JVM and into the Python interpreter so that your Python function can go and do its magic. And that means serializing, deserializing, and doing the whole thing again. So in our case, that means also serializing and deserializing the ground truth, which is quite an expensive operation. It's actually also why you can see it going up and up as the ground truth gets bigger and bigger, because it just is bigger, more to serialize. So we spent some time trying to figure out workarounds. To head off the obvious question here, why not use the new Pandas UDF? So the new Pandas UDF will give you mostly optimizations based on the fact that it won't do the UDF on a row-by-row basis. But for streaming, in this case, our one name, whether you do that as a chunk of one name or as a single row, it isn't going to give you anything. So we wouldn't expect to see major improvements there. One thing we will still try to investigate actually is whether the serialization to arrow and out again would be quicker than via pickle. So we're not quite sure on that yet. So some other things that we have been considering to get around this. So one thing we could do is, okay, let's get rid of this horrible Python UDF, because apparently it's bad, and replace it with a Scala UDF. So we've actually written a blog post on this again, on how you can use a Scala UDF in your PySpark code. It's really quite easy, and it can give you quite a big performance boost. The problem here is that our beautiful cosine similarity has been implemented in C++ for efficiency purposes, which then would mean that you'd also have to implement a JNI, a Java native interface connection to get at that C++ code from Scala. So not unfeasible, but a lot more work than you would think initially. Second option, map partitions for Python in PySpark. So this is not a trivial thing to implement. I know this is a discussion that's been ongoing quite long in the community. But we do feel it should be on the table, at least as an option, that we should somehow find a workaround for this, because fundamentally it would solve a lot of our problems. Third one, as Zhe already alluded to earlier, sparse matrix multiplication for Spark. If you go to the Breeze source code, the actual linear algebra library that Spark uses, you'll actually find a beautiful sparse matrix object and a multiply method. So initially you're thinking, hey, great, we're good to go. When you actually start reading the code, the first or second line says sparse matrix dot to dense, which basically screws you over, because it will then make your whole matrix dense again. So if we had this sparse matrix multiplication, we could actually make it work as well. Finally, the last one, which is a bit out of the box, is, okay, what about if we take that cosine similarity computation and just do that somewhere outside of Spark? Maybe we let it run as a separate service with a REST API, and you wouldn't hit any of these problems of this constant serialization, deserialization. In that way, you could just have the ground truth already available. So it's a bit out there, but it's something we're considering. If you know why any of these possible workarounds will work or won't work, please let us know. Or if you have some other suggestions, again, please let us know. We're very open to ideas. The final thing I want to talk about is to broadcast or not to broadcast. So as Zhe alluded to earlier, we broadcast the ground truth to our executors so that ground truth is available and that the computations are simple to do. So in the case of streaming, it's quite nice. Let's say somebody wants to match name 1, name 2. That arrives, okay, it goes into the executor. Our beautiful algorithm does its magic, and the names leave. So we're all good, right? So one surprise that we had there is that once that happens, Spark's context cleaner actually starts a timer, as it were. So the context cleaner's goal is to actually keep an eye on broadcasts and other blocks that are kept in memory and to be sure to clean them up if they're not being used anymore. So in our case, we have a long-lived Spark application that can see some load, but then once in a while will just be quiet. As we're mostly a Dutch bank and our users are mostly in Holland, you can imagine at night in Holland, people won't be matching many names. So what happens after a while is that our ground truth is gone. The executors will still stay alive because we've said we want a minimum of 2 executors to be there, but there will be no ground truth. So what happens now when somebody wakes up in the morning and wants to match name 3 and name 4, name 3 and name 4 will get sent to an executor for matching, but hey, there's no ground truth. So what happens now is we have to do a full rebroadcast of everything, which is a really expensive operation. So the first thing that will need to happen is that the driver will first need to figure out where all the partitions of the ground truth are, fetch them, pull them into the driver, and then broadcast them out to the executors again. So anecdotally, we've seen this to take about 30 to 40 seconds, which for a streaming application that you want sort of real-time results in is really quite killing. So again, name 3 and name 4. The beautiful, hacky way around this is to actually just use keep-alives. We've called them tracers. We just, every once in a while, we push a tracer through the system, and we basically keep the ground truth warm in that way. We actually also looked at marking the broadcast as non-cleanable or something like that, but that could also be tricky, because especially when you're using dynamic allocation, how could it then ever kill an executor if you're marking a piece of memory that you're saying, oh, you cannot clean this? So it's something you actually want to avoid, possibly. So overall, wrapping up, we've built a large-scale fuzzy name matching system, initially for batch, but we've now also made it possible to use in a streaming environment. Overall, we found Spark ML to be a really quite elegant and easy-to-use abstraction to build your data pipelines, to build your machine learning models. Combining Spark ML with structured streaming, at first it's really easy, and you're the small little kid saying winning. And then reality hits in, and you realize there are actually some nasty pitfalls that you can run into. And finally, actually monitoring the individual stages of your ML pipeline in structured streaming, we found actually to be quite challenging. We ran into several cases where we saw, okay, in Spark UI it's slow, but we couldn't dig into that and figure out which component exactly was slow. When we eventually did, we quickly realized what the problem was, but it took us quite some time to figure it out. So, on that note, thank you for your attention, and we're happy to answer any questions you might have.
I have a quick question. So, for what in a sense do you just do a cross join of all your names so that you have all the pairs like in the batch mode? Is that what you're doing? Like, and then you just calculate the cosine similarity and then basically just have a filter and say like if the cosine similarity is greater than certain range, and then you just like those will consider as candidates. Is that how it works, or?
Yeah. So basically it's the same thing. So you do the cross join and you do the two matrix multiplications.
Okay.
Yeah, and for the,
so you're not like doing any sort of locality sensitive hashing.
Yeah, in that time we implemented actually quite early, like 2016, 2017. At that time, the locality sensitive hashing was not in Spark yet. So, but yeah, definitely good to try. As far as I know, there is no cosine distance in the LSH, but yeah, we could use a
I was thinking you can just, if you already have the cross join, right, can you not just calculate the cosine similarity using UDF in Scala and just compare them? Wouldn't that be like pretty fast? Am I missing something? Why go through all this matrix modification thing? I thought that would be pretty easy, right? Because you're just tokenizing each of the names, right? Using space, is that correct? Is that how the token works? Like, maybe I'm missing is what is actually in the feature, like how are you tokenizing it and featureizing it?
Yeah, maybe we can talk offline. Yeah.
Okay.
So.
Yeah. Hello.
Hey.
On this side.
Oh, sure.
Oh, sorry.
Yeah, quick question. So after you, in the batch processing, after you get the matches, right, you get a probability, how do you deal with false positives? So if you have matches that are, both very similar, is it automatic resolution? You just say pick the best match, or?
Okay, good question. So actually, we have from the ground truth, we know which one. So we have an internal data test set. We know which one should match to which one. So after we get the top candidate and the best candidate, we can tune the threshold to decide, let's see, the cosine similarity is greater than this threshold, we think it's a match. Otherwise, we drop it.
Thank you.
Hey, so I actually had a similar question to the person who came before me. I gave a talk yesterday about a very similar problem. Our use case was different, so our solution was different. But I just wanted to confirm, you noted earlier on in the presentation that if we wanted to compare all 160 million incoming records to the all 10 million ground truth records, they would generate 10 to the 16 possible pairs, roughly. So is that actually how many pairs you're generating? You actually generate that number of pairs and go through all of them. Is that true?
Yeah. Yes.
Oh, okay, that's amazing. All right. That's all. Because we had to, in my presentation, I was like, oh, there's no way you can do 10 to the 16 pairs. So I talked about this technique called blocking to roughly cut out a large number of the pairs before you start actually evaluating them pair by pair. So maybe I should talk to you a little bit afterwards.
Hey there. We actually deal with a very similar situation at my company. And I guess my question would be, is there any particular performance or implementation reason why you chose to use Levenstein distance instead of an alternative metric?
For the Levenstein distance, for us, it's a kind of the runtime is unacceptable. Yeah. So basically, your question is about why we didn't choose a Levenstein distance?
Yeah, because after looking at it in our situation, which I think differs from yours a little bit, we actually settled on the Jaro, whatever you call it, distance. And we did see like gains in that respect. But again, maybe our situations are a little bit different, which is why I'm asking.
Yeah, right. So the way we choose a token-based cosine similarity will, the computation complexity is way more smaller. Because if we tokenize the names, let's say for the one word it has 5 names, another company names have 5 names. So basically it's just to do kind of some 5 times multiplications. But for the Levenstein distance, you kind of need to do the, I don't know, I don't remember the time complexity in my mind, but it will be more time consuming.
I see. Okay.
Yeah, we can discuss offline.
Maybe, yeah, I would love to. Thank you.
Yeah.
Yeah, maybe I missed it. How do you vectorize the names? How do you get the numbers?
The vectorize the name. So first we tokenize it. So basically, you can choose to use a word-based or like a character-based. Then we use n-grams to use 1 token or the bigrams, 3 grams. And finally, you can build a dictionary and use it. So this is a count vectorizer.
So frequencies of bigrams and 3 grams.
Yeah, kind of. Yeah, after you get the count vectorizer, we also use a TF-IDF, kind of our customized TF-IDF because we want to get rid of some stop words, such as some legal forms, LTD and BV. The weight of these words with these tokens should be lower.
Thank you.
Yep.
So I was wondering what's your latency when you were doing streaming, for the streaming application, what was the latency of name matching? Like what
So
is it?
you're asking about the latency end-to-end for the matching, or?
Exactly, so when you're in streaming mode.
Yeah, so again, it depends very much on the size of the ground truth. For our full ground truth, we found roughly 3 to 4 seconds
Okay.
total processing time.
And the deployment, so you were just using basically a Spark streaming. You were not using, it was the Spark streaming that was doing the scoring, right?
Yeah.
No other deployment, okay.
Yeah.
Cool, and also, just a comment.
Sorry, we're running out of time, so
Sure.
you could ask the second questions offline. Yeah, that's fine. Yeah.
okay.
We need to get
Yeah.
ready for the other speakers. Sorry. All right, so let's thank our speakers.
Yeah.